In this video, we will look at some problems that deal with valid parentheses, which are also known as regular bracket sequences. And we will look at 6 problems in increasing order of difficulty. And all of these problems, they have different approaches that you can take to solve this problem. The most standard approach is via dynamic programming and the stack data structure. That is the most common, and that is the one that you might be familiar with. But in this video, I want to show you a different perspective. I want to show you a new paradigm of solving all of these problems using data structures such as segment tree, binary search, and contribution technique. At first glance, these might seem like an overkill, that if you can indeed solve these problems using just dynamic programming and stack, why even apply segment tree or binary search to these problems? But the goal of this video is for you to learn new things so that the next time a problem on an RBS appears in a Codeforces contest, you don't have to think twice about how exactly to apply stack or DP to this problem. If you do understand how to apply segment tree or binary search to this problem, you will see that you can solve the problem within 5 minutes of reading the description. So in fact, you can try to pause this video and go through all the 5 problems that are written over here and see if you are able to solve all of them within 5 minutes using DP and stacks. If you are not able to do that, this video might be interesting to you because the segment tree and binary search approaches really make all of these problems trivial. So let's begin with the simplest problem first, which is level 0, which talks about how to check if a string is a regular bracket sequence or not. So this is your level 0. Level 0, check if string is RBS. How do you do this? You must know that this is the most classical stack based problem that says that every time you encounter an opening bracket, you push it onto the stack, and if you encounter a closing bracket, you pop a opening bracket from the stack. That is, you push this index to the stack, you push it to the stack. Since you saw a closing bracket, you pop this index from the stack, so this is now gone. And then since you saw another closing, you pop this element from your stack, and then you keep going. And then at any point of time, if your stack becomes empty but you have a closing bracket that needs to pop something from the stack, then the answer is no. Otherwise, the other criteria is that at the end your stack needs to be empty so that there are no opening brackets that are still remaining to be paired. So this is the most standard way to solve this problem. This is the boring and easy way. Now let me show you a transformation of this problem that will actually help us solve all the other 5 difficult problems. So this transformation is quite popular on Codeforces, where you say that you take this string, and we know that we don't have a lot of algorithms that can deal with opening and closing brackets. So why don't we convert it to a world that we are most familiar with? That is, why don't we convert it to integers? So you say that every time you see an opening bracket, you replace it with 1, you replace it with 1, and if you see a closing bracket, you replace it with -1. And then what is the necessary as well as sufficient condition for this integer array to represent a valid RBS? So some of you might know that there are 2 conditions, right? So first of all, I'll write down the boring conditions. Like, these are the standard conditions that you usually apply, where what you do is you track the running sum. So this is your running sum, and you see that if your running sum becomes less than 0 at any given point of time, you exit the loop early and you say that the answer is no. That is one criteria. And the other criteria is that at the end, your running sum should be equal to 0. This is how most people solve this problem even after this transformation. But this is not good enough, because doing so many complicated things, that iterating over an array and then checking something and then returning early and then checking something else at the end, that is too much steps. Can we simplify it down? Can we formalize this problem statement? Because if we can do that, only then we can apply some data structures and algorithms that we know. So how can you formalize it? So you can see that the necessary and sufficient condition can be stated like so. When you are computing the prefix sum, right, most people terminate early as soon as they see a prefix sum that is less than 0. But I say, why do you need to terminate early? Why don't you just compute the entire prefix sum? So this is the prefix sum array. And then once you have constructed the array, can't you just look at the array and deduce something from it? So tell me, what are the necessary as well as sufficient condition that you can infer by just looking at the prefix sum array? So how do you infer that at any point of time you dropped below 0? One fancy way to do that is to look at the minimum element of this prefix sum array. So if the minima is strictly less than 0, then of course your answer is false. Otherwise the minima has to be greater than or equal to 0. But then you also want the final prefix sum to be equal to 0. But notice that the final prefix sum is also a candidate for the minima. This means that the concrete conditions for a string to be a valid parenthesis is that minimum element of prefix sum should be equal to 0, not just greater than or equal to 0, should be equal to 0. This is first criteria. And second criteria is that last element of the prefix sum should be equal to 0. So some of you might already see that we are now entering the known territory of data structures and algorithm, because we are now talking about minima of an array and the last element of an array. So this can anyway be accessed in O of 1, and in this problem for the entire string, of course you can compute the minima in O of n for this entire array, and that's fine. But this will be the building block for developing the solutions to the harder problems that we see in this video. So now let's move on to level 2, level 1. So level 1 says that what is the length of the longest valid parenthesis inside that string. How do you compute this length? So now we have level 1. Length of longest RBS. So to compute the length of longest RBS, some of you might be aware that this is very standard dynamic programming problem. In fact, this is one of the first problems that appears on Codeforces tagged DP for a certain rating. And how do you do this? You fix any index R and you define your DP definition like so. You say DP of R is the longest RBS that ends at R. So if the RBS is ending at R, then you can inspect the element that is present at this location. It can either be an opening bracket, in which case this DP value would be 0, because no valid parenthesis can end here with an opening bracket. Otherwise, it is a closing bracket. So if it is a closing bracket, then you can notice one fact, that any RBS is nothing but a concatenation of several RBS. This is by definition. This might not be obvious to some of you, but it is actually true that regular bracket sequences or valid parentheses, they are by definition concatenation of valid parentheses. So if you have this valid parenthesis and if you have another valid parenthesis, it is easy to see that if you concatenate them, then they would still be valid, but it's not obvious to see that why it is also true that if you started with this, then you can split this apart and they would still be valid. But this is not a hard thing to prove, so I'll skip that. So since this is a concatenation and if this is a closing bracket, what you're looking for is that for this particular closing bracket, what is the closure? So a closure basically means, so what you are looking for is this closure. What is a closure? Closure is a substring that has all the matching pairs, and that is the smallest substring. So for example, if you find a matching pair like so, then you can say that this element is a closure for this element. That is, this entire substring is a closure. So you have to find out the nearest closure. What if you don't find a opening bracket immediately after? Then you can encounter a scenario like this. You find a closing and then you find another closing. Then closure needs to close everything that it has seen. So it has seen this and it has seen this. So it needs to find the closure of not just this, but also this. So suppose it encounters this, then you see that this matches this, but then the matching pair for this has not been encountered. So it looks ahead and then finally sees the matching pair like so. This could be one criteria. Other thing could be something like you have this closing, and it found it matching, but then another closing started. Then you also need to find you already found the closure for this. You are looking for the closure of this, but now since you encountered this element, you also have to find the closure for this. So suppose you get the closure like so, and finally you get the closure for the last element like so. So you can see that this string is the smallest closure that ends at R. So how do you compute the DP transitions? Then your DP transitions would be that suppose this is the smallest closure point. Suppose this is the nearest L that creates a substring L to R, that is a closure. This means closure substring means it contains all the matching pairs inside it. Then since RBS are just concatenation, you can say that DP of R is equal to R minus L plus 1. Basically, this last string is a valid parenthesis, plus you want to apply that same DP over here. You want to extend this substring as far as possible, plus DP of L minus 1. And what is your final answer? Your final answer is max of DP of R. Because the longest RBS has to end at any index, so you compute it for all the index and you take their maximum. So this is the standard way to solve it with DP. But how do you actually find out the closure? Like for each R, how do you know what is the smallest L? So it is not difficult to find the closure if you really understand how stack works. Because if you notice that when you do your string processing algorithm for valid parenthesis, then when you encounter this string, when you encounter this opening, you push it to the stack, and then you push this to the stack, and then you can see that you found a closing bracket. So this closing bracket will pop something from the stack. So the element that it pops, that element acts as the closure for this element. This is not obvious to see, but take a minute to pause this video and think about why whenever you are a closing bracket, whatever index that you are popping from the stack, that is your closure. Because if you are popping it from the stack, it means that you have created a matching pair. Then whatever was in between you, that must have already been a matching pair, and that's why they are not on the stack anymore. And since you have just created a matching pair, we were looking for a valid parenthesis that is of the smallest length, and that ends over here, and that is the smallest closure that you could get. And this manner, for you can pre-compute L for each R. How you can do that? Just run your normal valid parenthesis algorithm and keep track of which index popped which index. So if you are a closing bracket, then whatever you pop is your L, and that L will be used in this DP computation. So this is level 1. Sure. Now this level 1 also has a fancy data structure solution, but I will talk about that later when we talk about more difficult problem, but we will come back to it later. Right now the stack and DP approach works just fine. Now let's look at level 2. So in level 2 you have to count the number of regular bracket subsequence strings. So for level 2, let's define it like so. Count RBS substrings. How do you do this? Again, you can use the same DP idea as before. You define your DP definition like so. You say DP of R represents the longest valid, DP of R represents the count of RBS substrings ending at R. Previously we had defined it like so. What is the longest RBS that ends at R, and this time we are saying that that same DP will represent what is the number of RBS that ends at that index R. How do we populate the DP values? Again, you can see that if this is your index R, of course, if you encounter an opening bracket like so, no substring can end over here, that is an RBS. So DP value is 0. Otherwise, you then encounter a closing bracket. So if you encounter a closing bracket, then let's find the nearest closure, because you will need that closure to find the smallest string that is still an RBS. So suppose this is your closure, then you have two options. Either you can take this closure string as one valid RBS, because closures are also RBS, or you can compute all the valid RBS that ends at DP L-1, that ends at index L-1, and you can append this closure to all of those substrings, and then you would now get a substring that ends at this location. So this time DP of R is equal to 1. So this 1 means you decide to keep this closure separately, that is a fresh substring, or you decide to merge this closure with your left neighbor, and your final answer is summation of DP of R. So this is also an easy problem to solve using stacks and DP, because again this L is nothing but your closure point, and this closure point you can get when you do that stack algorithm. So this is just same as before, but instead of computing the longest, we are now counting the total number of valid substrings that ends at that location. Now let's move on to level 3. So level 3 says check if a substring is a valid parenthesis or not. So this is level 3. Check if substring S from L to R is RBS. How do you do this? Now for this problem, I would have to admit that I could not find an easy solution for this, because for these two problems I told you that there are easy solution that uses stack and dynamic programming for these two problems, and there are other fancy data structure solution as well. But at least for this one, I am not sure if there is an easy way that just does it via stack or two pointers or something. I think there could be, but at least I'm not aware of that. So do let me know if I am missing something very obvious, and if there is a very easy solution for answering this without any fancy data structure or not. But this is the problem where I'll introduce these fancy data structures. Now, let's see how you would compute this substring from L to R, whether this is an RBS or not. So if this is your index L and this is your index R, and you are looking for this substring. Now, remember, these were the two necessary as well as sufficient condition for the string to be RBS. That is, the last element of the prefix sum should be equal to 0. This basically means that the sum of all elements should be equal to 0. So let's say that we have already computed the prefix sum of this array. Then what does this condition translates into? It says that the last element of the prefix sum should be equal to 0. But you know, the one thing about prefix sum is that if the prefix sum at this point, if this prefix sum is equal to offset, then this offset will be added to everything in this range, right? And that is how you know that trick that if you want to compute the subarray sum, you first compute the big sum, which is the prefix sum at this index, and then you compute this offset and you subtract it so that you get the subarray sum over here. So if the last condition says that the last element of the prefix sum should be equal to 0, here you can say that the last element of the prefix sum should be equal to 0, but every number will be incremented by offset. So the last element of the prefix sum should be equal to offset. So this part you can check very quickly because you already have computed the prefix sum. So this is second condition is very easy to check. How do you check the first condition? It says that the minimum element of the prefix sum should be equal to 0. But then I told you that every element has offset added into it. So this means if the minimum element in the original configuration was equal to 0, then since it must have added offset to it, then you can claim that the minimum element should be equal to offset. And now you can see that it is very easy to answer this both of these criteria. Why? Because this second criteria, it's very easy to answer because you just have to check if the prefix sum of R is equal to offset. This can be done in O of 1 because you have already computed the prefix sum array. How do you compute the minimum element and check if it is equal to offset or not? This time it's simple. All you need is a data structure that can give you range minima, and that is nothing but a segment tree. So this is where fancy data structures start entering the arena. So you can either use segment trees, or you can also use uh, sparse table and any other RMQ data structure. And then you can see that you can now answer this query in O of log n. Now, I'll be honest, I don't know whether there is another simpler solution that does not use segment tree. But you can see that even if there were a simpler solution, if this problem arrived in a contest, in a Codeforces contest, I would definitely go with the segment tree approach. Why? Because I can use this as a black box and it is so simple to implement. All I have to do is just check if this prefix sum is equal to offset and check if the minima is equal to this offset, and I am done. So I can answer this query in O of log n. So you can see that segment tree is already turning out to be very powerful in these kind of problems. So now I told you that we'll come back to both of these problems after we learn about segment trees and how to apply it in this scenario, right? So let's see how we can solve these two problems without using stack and without using DP. So this time we'll use contribution technique and we'll try to find the answer for both of them. So first we want to find out what is the length of the longest RBS. So let's see how we can do this. So we want to revisit this part. One second. Yeah. So we want level 1.1, or let's say, yeah, it should be level 1.2 because level 1.1 was length of the longest RBS, right? So level 1.2 would be again a length of the longest RBS fancy way. Now, how do we solve it with data structures? This time, let me fix the left endpoint, and this time I'm not going to use stacks at all. So suppose this is your left endpoint, and let's define a DP definition. And even though I'm calling it as a DP definition, it is not really DP in a way, because you'll see that it is mostly contribution technique in 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 play. But this DP definition just helps to signify what we are trying to compute, even though we will not be using the answer from the sub problems. So we'll say that DPL means what is the length of the longest RBS that starts at this index. It can end at any index on the right hand side. Now just using these two criterias, right? And the criterias were, let me bring over the criterias over here. These were the criteria that the minimum element of the prefix sum should be equal to 0 and the last element of the prefix sum should be equal to 0. How do you how do you solve this problem? Just by looking at this criteria. So if you are familiar with binary search, you can see that first you start over here and let's look at the last index, right? So this, suppose this last index is n, this is the last index, then you want to find out what is the longest RBS. Then instead you can first split this range in half. This is your midpoint M, and then you can check whether this string is RBS or not. Because if it is not an RBS, if the answer is no, then you know that this bigger string also cannot be an RBS. But if the answer is yes, then remember I told you before that RBS are concatenation of RBS. This means that as long as you keep the starting index same, if the starting prefix is same, then this, if you take a prefix, right, and this prefix will never violate these two conditions. This prefix, not all the prefixes will be RBS, that is for sure, but none of the prefix will suddenly start violating the condition just because you remove the suffix. So this means that if you split your range at the midpoint and you try to figure out whether this substring is RBS or not, if the substring is not RBS, then no need to look on the right hand side because this has already failed the criteria. So you start by splitting it again over here. Otherwise, if the answer is yes, then no need to look any further. You are sure that this particular substring is still an RBS. So this means that we can now do a binary search on this entire string, and for every binary search you would have to use your previous sub problem, which was this, that is, can you quickly check whether this substring is RBS or not, and we already know that there is a way to do it via data structures in O of login. Then you can see that we have solved this problem in O of n log n into log n. We have solved this problem in log n into log n. Why? Because for each index L, you are doing a binary search for splitting the range in half and querying whether this L to midpoint is the RBS or not, and answering this query itself is O of log n. So that is why this is your final time complexity. Now, if you have just been watching the video so far, and if you are agreeing with me on everything, then you will be surprised that whatever I have discussed so far, that is not actually true. That has a very tricky bug that might not be apparent. And since you are just watching the video on casual mode, you might not have noticed. And the bug is that when I fix this index L over here, and I claimed that if your midpoint is not an RBS, if this is your midpoint and this is not an RBS, then we claimed that since the condition has already been violated over here, even if you extend it further, it will not be an RBS. That is what we said, and that's why we said that you could actually trim this range in half. But this is not true, because, and now we will get into some more nitty-gritty details of it, because the conditions, there are two conditions. So one is a strict condition. Let's define this as a strict condition, and let's define this as a weak condition. So you will notice that if anybody violates the strict condition, that is, if their prefix minima, that is, if the minimum element in the prefix sum array, if this drops below 0, if it becomes negative, then no matter what you do on the right hand side, it is guaranteed that it can never ever be an RBS. But this condition that you just saw, that the last element of the prefix sum should be equal to 0, this is not a strong condition, because as long as nobody has violated this condition, if their prefix sum has not fallen to smaller than 0, then the maximum prefix sum, right? The minimum element of the prefix sum, right? It could be, suppose it is 5. What does this mean? If it is 5, it means that there are 5 opening brackets that are yet to be paired. This means that if you extend this further, if you extend this string further, you can get the matching pair for all of these 5 opening brackets. So in fact, when I say that this condition is strict, this time I actually mean that this minimum element of the prefix sum should be greater than or equal to 0. So remember when we were discussing the first version, in the first version I said that it looks very simple. The criteria is that you might think that everything should be greater than or equal to 0, but then I showed you that the last element will be equal to 0. So that's why this condition turned out to be as simple as equal to 0. But actually, if you want to make it as a strict criteria, then you have to have this as your strict criteria, that the minimum element in this prefix should not fall below 0. They can be greater than 0, that's fine, because then you can extend this prefix and you still have the possibility of converting it to an RBS, right? So this strict condition ensures possibility. That is, if you fail the strict condition, then you are out of the game. But if you pass the strict condition, it is not guaranteed that you will be an RBS. You still have to pass the second condition. That is, the last element of the prefix sum should be equal to 0. This is the weak condition. So now, how do we solve this problem using this idea? Because we have just seen that our binary search approach was actually incorrect, right? So how do we come up with an algorithm that takes care of this weak as well as the strong condition? So let's try to look at the strong condition and let's see what parts can we actually discard, because the last time we discarded a mid where the prefix sum was not equal to 0, which we shouldn't have. Prefix sum could be greater than 0, that's all right. So let's only focus on this strict criteria, right? So this is the strict and that is the weak criteria, right? This is the strong criteria and that is the weak criteria. So you can see that you can still apply the binary search trick. You can split your range in half. This is your midpoint. And you can see whether your strict criteria has been violated. That is, in this subarray from L to M, what is the minimum element? If the minimum element is strictly less than 0, then this entire thing is out of the game, right? I mean the right hand side is out of the game because you cannot extend this string further. So you only have to split your range to make it even smaller. But if the minimum element in this range is greater than or equal to 0, it means that all of these indices that you see over here, this is your L. Then if you have partitioned this at this midpoint, then you can see that all of these indices are safe. That is, they are possible candidates for becoming the RBS. Now you can notice one thing, that this safe is monotonic. That is, it this element will be safe, this element will also be safe, this element will be safe, this element will be safe, this element will be the safe. The first time an element becomes unsafe is the point where the prefix minima becomes less than 0. Then if this has become unsafe, this is also unsafe, this is also unsafe, this is also unsafe. So that is why you can see that binary search can be applied over here, because the sequence looks like safe, 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 and then unsafe, 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 etc. So you can find, with binary search, you can find out what is the first position at which it gets unsafe. And then you only have to focus on this left area. But then we still have to solve the second part of the problem, which is, sure, if you can, sure, with binary search you can figure out what is the unsafe index, right? With binary search you can figure out with this L. If this is your L, you have figured out that all the index from here to here are safe, they are safe. And how did you figure this out? You did a binary search, and then in that binary search you used a segment tree to query the prefix minima. So computation of this safe has already taken you log square n time. But assume that you have computed all of these safe indices. Now how do you compute how many valid RBS are there in this range, and also how do you compute what is the length of the longest RBS? In fact, in this video, in this version itself, we'll solve not just the length. You will see that with that same trick, you can also find out the longest RBS as well that starts at L. And for to do that, you know that you have to make the prefix sum equal to 0. But now notice that all of these elements, they already satisfy the strict criteria because they are safe. So if any of them satisfy the weak criteria, that is if their prefix sum is equal to 0, then you are done. You can definitely be sure that that will be a valid parenthesis. But I already told you that if you are dealing with this L, then the prefix sum so far should be considered as this offset. And of course, when we are doing this minima computation, we should be looking not for 0. So you can see that 0 starts kind of like O. So you can see that it should be greater than or equal to offset. And similarly, the final, the last element of the prefix sum should be equal to offset. Right? It should be equal to offset. Now, how do you find out all the elements in a range that are equal to offset? Now, for some of you, as soon as I ask this question, how do you find out all the elements in a range from L to this that are equal to offset? For some of you, this might be very obvious, and for some of you, the algorithm might be completely new. So let me talk about it. So in this prefix sum array, this is your prefix sum array. The usual binary search etc that you do is you try to do a binary search if the prefix sum array is sorted, which in case you are not aware, for positive integers the prefix sum array is already sorted by default. So you can actually do a binary search on the prefix sum array using upper bound and lower bound, and that is a very fancy and useful trick for lower rated problems. But in this case our prefix sum array would not be sorted. But there is another way to do a binary search, not on the values but on the indices, and I see that not a lot of people know about this trick. So binary search on indices, what does this mean? This means that when you were computing the prefix sum array from left to right, if you stored value a over here and you stored b and stored a over here, you stored x, you stored y, and then you stored b over here, what you do is you create an adjacency list style vector, just like you do for graph. So you can see that their total number of unique prefix sums can be at most n. So you create n different map, sorry, you create one map with which can hold at most n entries, and in each map the key would be the value of the prefix sum. So this is the key a, this is the key, this is the key, and this is the key, and the value would be a vector containing, this vector would contain what are the indices at which this prefix sum appears. So you can see that when you start the computation from left to right, you will anyway insert these in increasing order. So 1 3, for b you would insert 2 3 4 5 6, 2 and 6, etc. And now you can see the fancy trick that these, for each prefix sum, all the indices are sorted, no matter if the original array contained positive or negative integers. And then you can actually do a binary search using upper bound and lower bound. You don't actually have to implement the binary search yourself. So then coming back to our original problem, how do you find out the longest subarray that is an RBS but starts at L? So everybody in this safe zone, they satisfy the strict criteria, that is they are greater than or equal to offset. But now they must satisfy the weak criteria, which is that they should be equal to offset. Only then they will be a candidate. And how do you do that? You just look into the map that you have created, you locate offset, this offset will contain a list of vectors which will be very long, but at some position some of the numbers will be less than L, some of the numbers would be if this is L and if this is your safe index S, then if this is L and this is your safe index, then some numbers is here 5, 7, 9, 22, etc. And suppose L is over here and safe is over here, then what you are looking for is you are looking for the maximum number in this vector that is less than or equal to S. And how do you do that? That is nothing but the classic lower bound. You just look for the you do one thing, you do upper bound of S and then you go one step back. So in fact this is also a trick I see not a lot of people are aware of. Like everybody knows how to compute the first occurrence that is greater than or equal to X, but how do you compute the first occurrence that is strictly less than X? Or how do you compute the last occurrence that is strictly less than X, right? So in fact here you can see that this is S plus 1, so you want to compute the last occurrence that is strictly less than S plus 1. So what you do is you find out the upper bound of S plus 1 and then you do ITR minus minus. So with in log n you can query what is the longest thing that is available over here in the safe range. So this is the safe area, this is the safe area, but in this safe area the prefix sum of offset is achieved only over here. So this means that this is the longest RBS that starts at L and ends at over here. And now you can already see that with this trick you can also solve the problem of counting the number of valid RBS that starts at that index L. How do you do that? This time you have already computed. This time what you have to do is, since you have located the vector that contains all the indices where this offset is achieved, what you are looking to find is how many integers in this vector fall in this range L to S, and this is your classic upper bound minus lower bound trick. So in case you are not aware, this is a very famous problem that you can answer if you want to find all the elements in a range x to y. You just do a binary search and then you do a upper bound for this and then you do a lower bound for this and then you subtract them, and using in log n you can answer this problem as well, this count RBS. So you see that it was a bit of an overkill, but it was a novel idea nonetheless. And you will see why this having this approach actually simplifies a lot of complicated problems that might have a simple solution, but you can just apply this binary search trick and standard data structures and upper bounds and maps to solve it quickly. But we still have to address one thing, that the time complexity is n log square n and the dp plus stack was giving you O of n, which is not bad, I would say. See, O of n and O of n log square n doesn't really make that big of a deal, to me at least. But in fact, it is possible to reduce the time complexity to just O of n log n. And this is another level of understanding that you need to have about segment trees to do that. In fact, you can do this even if you use it as a black box, because the reason why I'm creating this video is because I want you to learn all the functionality that that black box exposes. So everyone thinks that in order to reduce the time complexity of binary search over binary search inside binary search, because here what you are doing is you start with an L, and for locating this safe thing you split the midpoint in half, but then you are querying the prefix, you are querying the minimum element, so then you split it in half. So you are doing a binary search inside a binary search. So segment trees are actually equipped to handle doing binary search inside a binary search, and most people think that you need to know the internal details of segment tree to do a walk on the binary search to do a walk on that segment tree to achieve this n log n time complexity. That is not true. In fact, you can achieve this n log n time complexity using at coders exposed methods for this black box, which says that the name of the function is very conveniently max right. It says that, in fact, this problem is a very good fit for this. It says that if you have an array and if you have defined a segment tree over it, and if you want to partition it like so some of the indices are safe, these, so if your prefix is safe and your suffix is unsafe, right, then instead of trying to locate what is the safe index yourself by splitting the midpoint and then querying the segment tree to again query the maxima, you can just ask it to give you the what is the max right position of the safe index, which is over here. So at coder's segment tree, it just accepts this max right, it just exposes this max right, which accepts the boolean function which you have to define, which talks about whether this how to tell whether a prefix is safe or not. And how do you know whether a prefix is safe or not? If their maxima, sorry, if their prefix minima is less than offset or greater than offset, accordingly you can decide. So all you have to do to achieve this time complexity is stop doing binary search yourself, and that would actually make the code simpler instead of making it more complex, because previously you were defining L, R, and then you were doing while L less than equal to R, and then you were doing the binary search. But this time you just give the segment tree library your L, and you define what your predicate is for defining what is the safe prefixes are and unsafe prefixes are, and it will spit whatever the last occurrence of the safe index is. So you can do that you can do that in login per query, and in this manner we have solved both of these version, that is length of the longest RBS in login and count of the RBS in login n log n, overall time complexity. So it's not bad, going from n to n log n is not bad as long as you have clarity. And in fact, I would say it's a good exercise for you to implement max write function, because max write was actually designed for doing a binary search inside a binary search, and this is a classic example of doing that. So, okay, now if you have really understood segment tree and binary search inside a segment tree and these data structures, then look at the last two problems on your screen and try to pause this video and try to think of the solution. If you really understand it, you should be able to solve it within 5 minutes. If not, I'll anyway discuss about these problems for a short while. So in this version, here you are saying that you want to flip every element in this range from L to R, and you quickly want to find out whether the original string can still be an RBS. So let's talk about level 4. Level 4, flip this subarray is original string RBS. And what do I mean by flip? I don't mean reverse, I mean flip. That is, if this subarray L to R looks like this, opening, closing, opening, closing, something like that, then you can flip everything. So this is opening, converted to closing, this is opening, converted to closing, this is closing, converted to opening, and so on. So after doing this flip, is the original string an RBS or not? And you can assume that the original string was indeed an RBS, otherwise the answer will of course be no. So in fact, it's actually given to you in the problem that the original string is an RBS. Then how do you solve this problem? One thing you can notice that you want your final prefix sum to be equal to 0. So let's compute the sum of this area and this area, and let's call that sum as out. And let's compute the sum of this area and let's call that as in. So you see that out plus in must have been equal to 0. And by sum I mean this replaced with plus 1 and this replaced with minus 1. But now if you flipping everything, what does it looks like in the world of data structures and in the world of arrays? So flipping means multiplying everything by minus 1. So if the original sum was in, then the new sum would become out minus in, and this should also be equal to 0. But since both of these quantities are equal to 0, outs and outs cancel out, and you see that in is equal to minus in. So which number is equal to negative? It's only 2 into in is equal to 0. It means that in is equal to 0. This means that first feasibility check is that whatever substring that you are asked to flip, their sum should be equal to 0, and their sum you can anyway figure out how, by prefix sum. We already told you before that if this is your offset, then the last prefix sum, which is prefix of r, should be equal to offset, so that the sum becomes 0. So if that condition is not satisfied, of course your answer is false. Otherwise, assume that this entire substring does have sum equal to 0. Now, how do you ensure that the original substring will still be an RBS after you do the flip? To do that, you can maintain two versions of the prefix sum array. The version P original would be just the original prefix sum, that is opening replaced with plus 1 and closing replaced with minus 1, and you maintain P star, which is the inverted version, wherein you replace opening with minus 1 and closing with plus 1. That is the inversion of the entire string. You store the prefix sum array. Then if you want to make the entire string an RBS, you can see that since you have not changed this part, it will not matter, right? Now this part will still satisfy the strong or strict criteria that you have for RBS. Now what happens when you go inside this substring? Now if you go inside this substring, you have to make sure that how much balance you have accumulated so far, what is the offset you have accumulated so far. So you can see that the offset is nothing but the sum of all of these entities that you have accumulated so far, which is nothing but prefix of L minus 1. So this is the offset that you have accumulated so far from the prefix 0 array. So if nothing was flipped, then you would have wanted your minimum element of this prefix sum array to be greater than or equal to offset. This is what you would have wanted. But now that everything has been flipped, then in the flipped version of the prefix sum array that you are maintaining, in this flipped version, you can still compute the minimum element over here, but you can notice that this minimum element includes this offset from the flipped version, right? So if you subtract that offset, it will give you the actual minimum sum that is achieved starting from here, and that minimum sum, that is subtracting this. You compute the minima, you subtract the offset from this p star, and you get some quantity. That quantity should be greater than or equal to offset. So this time not just prefix of, not just the minimum thing should be greater than or equal to offset. This time the minimum thing minus this offset, so that you can get the actual thing. That actual thing should be greater than this offset, because this offset will actually be added to everything over here. So if it is greater than offset, then their sum will not be strictly less than 0. And since anyway the overall sum is equal to 0, this means that once you cross this, your total prefix sum is same as what you had over here. So you can pretend that this block did not exist, and then this will not affect this suffix as well. So this means that you can, all you have to do is compute the minimum element of the prefix sum array in the inverted version, subtract the inverted offset, and then the number that you get, you have to compare if it is greater than the original offset or not. So you see, with this you can simply solve it in O of log n. Now there could be, and I know that there is a way to solve it without using segmentary or binary search, but we'll not talk about that in this video. Do let me know in the comment section if you have a fancy way to do it without segmentary. And finally, for the last version, that is how many how many subarrays are there that can be flipped while still making the original string RBS. So this is just the contribution technique version for this, just like this was the contribution technique version for this. So this time you have to find out how many valid pairs exist. How do you do this? So for this version, this is level 5. Count valid LR that can keep S RBS even if you invert the substring. How do you do this? Again, you can define your DP definition like so. You fix your index L and you say that DP of L would mean how many valid pairs exist such that their left endpoint is L. So this is classic contribution technique. And then you want to know what is the, again we have to use that same safe concept, right? You want to know where is that strict criteria being violated, right? So if this is your offset, right, if this is your offset, then regardless of what you are comparing it against, you are comparing it against the original offset, right? But it doesn't matter because the minimum element is the minimum element, right? That doesn't change. So what you are looking for is what is the minimum element in this range, and is it greater than offset or not? Like where is the first point where the minima falls below offset? So these prefix will be safe and this suffix will be unsafe. So again, you can use binary search inside the segment tree to query this in O of log n. Or if you don't want to do that, you can do a manual binary search and then use this segment tree to query the prefix, to query the subarray minima. And once you have found out all these safe indices, then what you are looking for is in this safe region, you are looking for what all indices are there where this offset is actually achieved, so that you can create the sum as 0. Remember that sum as 0 was the criteria. So what are these indices? And we have already told you that you can do this via the trick of maintaining a map of prefix sum, and you locate the offset index, and then you locate the vector corresponding to it. It will have the sorted indices, and you just have to use upper bound minus lower bound to count the number of indices that are in this safe zone. And that's how you can compute each dp of L in log n, and overall time complexity becomes O of N log n. So you see, with the knowledge of data structures, binary search, segment tree, contribution technique, dynamic programming, and stack, all of these problems become very trivial. Now, I know that in this video I have kept things very high level. I have not shown you any code of how to store these maps, how to do the upper bound minus lower bound binary search, how to actually use the max write, etc. So I have not done that intentionally in this video because I did not want to keep this video too long. I wanted to just be about ideas. The implementation detail, I have actually created a blog on my website. So I have created a tutorial on my website. I will link it in the YouTube description. And in that tutorial, you can actually find out the concrete code that you can use to do max write thing like binary search inside binary search. And you can find out the actual code that does the computation of this safe index, storing it in map, upper bound and lower bound, and so on. And in this YouTube description, I will also link down the problem that you can submit on Code Forces for these three variations. The variations, this one, length of the longest RBS, and level 4 and level 5. These two problems, I will link them in the YouTube description. Feel free to absolve it and let me know your alternate approach if you have any. In fact, I have also created a dedicated video for this part, length of longest RBS, where I talk about how to find out the closure of each closing index. So I will also link that video in the YouTube description. You can go and watch it. So do let me know in the comment section if you have any other useful tricks for RBS that you want to share with the community. And I just found these tricks helpful, so just decided to create a video around it. That's all for today. Thank you.